and we're solving the puzzle for day 8 in Adventure of Code. In ResonML, where I'm still learning ResonML, or ReScript as it's rebranded. And today's adventure, I've been copying and pasting some basic data here, and I've been so I just set up a file that we can run. I'm just gonna paste this. There we go. So that was the test data that we got from our Adventure of Code page. Yes, so Adventure of Code today is basically a handle halting. So what it is, it kind of boils down to that we're supposed to execute some assembly-like instructions, if you will. And there's basically three different instructions. We have accumulate, which increases a single global value, which would be in a CPU, I guess, a register or some address in memory. We have a jump instruction where we can jump to another part of the program, and we'll have a noop, which doesn't do anything, it just executes the next line. So here's an example that we're starting from. We have a few instructions here. We do some jumps, and our mission is that this is not a really well written program, that it loops. So in this case, we do noop, we accumulate 1, we jump to 4, so that's +4 relative, so 1, 2, 3, 4, we accumulate 1, we jump back -4, which is over here, and then we jump -3, and then we kind of begin to do this all over again. So the idea here is to break the program once we loop. So as I understand things, is that we're supposed to halt the program as soon as we pass an instruction that we already been executed once. To me, this kind of seems like an easier problem than the one from yesterday with the whole graph. I actually went back and redid it and pushed it to my Git repository, just for my own sanity. We had I kind of made an abstraction for a graph that I worked with instead of our regular. I'm not sure what you want, Linus. What's up, chat? So anyway, yeah, that kind of got me off track a bit. But so what we want to do is execute this and basically halt the program and look into what's in our accumulator or our global state once the program finishes. So I guess the program won't finish unless we track it somehow and introduce a break. And so this is the sample data. This was supposed to produce the number 5. So let's work with that. So this is supposed to produce 5. So we're just gonna do some basic stuff here. We're gonna import our data just for later, and we have our data file data day 8, so that we're gonna use later. I created that one. We also have our Adventure of Code module, which has some nice helper functions. So I guess the first things we want to do, looking at this, is that we want to have, so this kind of boils down to actually making some sort of interpreter, I guess, a simple notion of it. So I'm gonna create a type instruction, which is one of the following. So it's either noop, we don't do anything, and that takes an int, or we have a jump or accumulate instruction, which also takes an int, or we have a noop. No, that was the first one. We have a jump instruction, which also takes an int. So in this case, the int means that we jump relative where we are. Accumulate means that we're accumulating the integer into our global state, and then we have our loop instruction that doesn't do anything with anything. It just keeps on going. And then we also want some sort of state. So let's create that one. Type state, which we define as just a integer, I guess, or yeah, let's call it accumulator. This would probably then be equivalent to something on the processor, like a register or something in that of that nature. So we'll say that that's an int. Okay, so now to parsing the program. So we have our string, which we want to pass into our nice function split, and we want to split this on new line as per usual. I'm gonna treat myself to a beer here. Actually, I kind of wished I had one yesterday when things went south on me. Yeah. So we'll split the string, and so now we have each row, and from this we want to map to an instruction set, or to a set of instructions rather. So this we map. So we take a line and we want to produce something here. So in this case, each instruction is nicely parsed. They have they basically consists of two things delimited by a space. So we so let's create our pair. So that would be the string passed into our split, and we'll split it on a space this time. So this will create our pair, and our int, or our I, so let I, so that would be the plus or the minus thingy here. That is basically, or that comes down to being the pairs nth. So the second argument of this string, and the first, and then we have to parse this into some sort of instruction, right? So we'll add a switch, and here we grab the list nth pair 0. So that would be this first portion, and here we have to account for all cases. So we have noop, we have accumulate, and we have jump. Yeah, and we also have to account for all the other cases. So we're actually going to add a different operator here just for our own, just to make this easier to work with later on, so we don't get any errors. Yeah, so for noop, we just pass or map this into a noop of I. For accumulate, we map this into accumulate of I, and a jump we map into, oh, kind of misnamed this, jupe. We map that into jump of I, and if it for some reason is something different, we just so this won't actually happen, but we'll add this for good measure. Okay, so now we have our program, or it's supposed to be our program anyway. So let's inspect this. So we can just pipe this into js.log and oops, see if this runs. No. Oh, right. Yeah, so here our I, we just grab the the second int. We didn't actually convert it, so that's a string, so we didn't actually convert it into a string. So we have an int of string. Yeah, so now we have tag 0 in our head, and that's a noop, and that corresponds to our first noop here, and we have the number 0, and so on and so forth. So I probably could, I have a nice list printing function here that I created. Yeah, so here we see that the tags, which translates into a number because JS, well, it compiles things. And then we have our arguments, I guess, to this. Okay, so now we have our program. And now we want to execute this. So we have some sort of runtime, or we want to create some sort of runtime. So let's call that exec. We're not really sure what arguments we're gonna take yet. But so this portion is supposed to be the function that execute things, right? So we definitely wanna pass in our program. So that's gonna be the reference. So that's basically a list, and the idea here is, for example, the jump instructions. So if you know on what line you're executing something, and then you want to jump, you just add your line, and you add the difference or the I of jump, and you go there. So we definitely want to pass in our programs so we know where we're jumping around to. We want to pass in our pointer, I guess. Good name to call it. So the pointer to what line we are currently executing. We want to pass in our state. I called it state up here. That's probably not. Let's call it register. So we want to pass in our state, and yeah, so we'll see how that goes. Okay, so and the idea here now is to basically do something like this. We pipe in our program into exec. We want to start off with our pointer at line 0. We want to start our program at line 0. We want to start at a state, so that's the accumulator. So we want to start with our accumulator set at 0 because that's the number that we're looking for eventually. Yeah, right. So we also need some sort of, so the idea here is to break the program when we reach a pointer that we already seen once, right? So here I'm gonna pass in our trace, some sort of stack-ish that keeps track of what pointers we've already seen. So that starts off as an empty list. So the program we pass into exec, which takes a pointer to our initial state, the accumulator, and our trace. Right, so this we probably want to recurse over. So the first thing we want to do is have a break criteria. So if the pointer is already in trace, then we kind of know that we just want to return our state, because then we're done, because we've looped around and the program is finished, or that's the exit criteria anyway. So I think there's exists maybe, yeah. So there's so if the trace is just a list of integers that contains the pointers that we already visited, so this exist takes a boolean or a true or false function, I guess. So if I equals pointer, then we'll basically just return our state because we're happy with this. Otherwise, we have some job to do. We actually have to execute things. So the instruction ints. Let that be list nth of program and pointer. So our instruction we want to execute is the nth row in program. And from here, we want to do a switch statement on that instruction. So this now contains one of these instructions. So we have accumulate, or let's start in the order. Noop I, we have accumulate I, we have jump I, and we also added our instruction unknown, which shouldn't really be executed at any point. But if it is, let's just call that a noop. We'll ignore the instruction and move on. And here from the noop, we don't really need our I, so we'll just ignore that. So what happens in noop? So in noop, we do nothing and we just execute the next stage of this program. So that would be exec, and our pointer, we would increment by 1, so we move on to the next row. Our state remains the same. Our trace, we definitely want to add the pointer into our trace. So let us overload this trace. So trace list append, and we'll append our current pointer. So this would create update the trace, or not update it, but rather overload it. So we're using the new trace in the next function, and we'll pass in the program as well. Okay. Yeah. So this would be a noop. Our accumulator would do the same thing, it just as noop, in terms that it just advances to the next stage, but we do want to update our state. So our state here would be state.accumulate plus I, because that's the number that we got in from the instruction. We'll pass on the state, we pass on the trace, and we pass on the program. And for the last portion, it's pretty much the reverse of the accumulator. Well, not really. We'll just keep passing on the state. It doesn't update the state in any manner. But what it does is that it jumps in another direction. So it takes the pointer and append or adds I to this. Yeah, so I feel that this might be doing something. So the breaking condition is that when we do find another pointer, we kind of returns. So that would return the state. So that's the only thing that really returns. And that will, through the recursive chain, pass on its way up. And now we have nice tail recursions since we don't append anything here. All right. Do I have format? Oh well. All right, let's see what errors I have gotten myself into. There's usually something. So there seems to be missing a parentheses here. Right. Okay, so it executes. So let's log this. So this returns 5. And that was what we were expecting from our test input. Okay, seems nice. Yeah, so now our idea here is just to switch out this to data.string, which was our real file with all our instructions. And we'll see how that goes. So now I have 1548. So that's a number. Hopefully it's correct. Let's just clean up this a little bit. Is this? Yeah. There we go. Log 2. This is the first portion of this. We also have, yeah. Okay. So this hopefully is our answer. So let's check. Gold star, yes. Okay, on to part 2. See what this entails. Oh, okay. After some careful analysis, we believe that exactly one instruction is corrupted. Somewhere in the program, either a jump is supposed to be a noop or a noop is supposed to be a jump. No accumulator instructions has been harmed. The program is supposed to terminate by attempting to execute an instruction immediately after the last instruction. The program is supposed to terminate by attempting to execute an instruction immediately after the last instruction in the file. By changing exactly one jump or one noop, you can repair the boot code and make it terminate correctly. For example, consider the formal program above. If you change the first instruction noop to a jump 0, it would create a single instruction infinite loop and never leaves the instruction. If you change the almost any of the jump instructions in the program, it will eventually find another jump instruction and loop forever. However, if you change the second to last instruction, jump -4, the program terminates. Okay. After the last instruction, the program terminates by running the instruction below the last instruction in the file, which changes it then contains the value 8. Aqu1 jump +4. 1, 2, 3, 4. Aqu1. So there would be 2 in the accumulator. Then we'll add 6. Okay, so to fix the program, so exactly one jump to noop or noop to a jump. Okay, so the first portion seemed pretty straightforward. This, I'm not sure how to approach. So, looking at the data, it's a jump instruction that. So it seems that it should be. I mean, So, I mean, we want to find an actual algorithm that does this and not just toy around, I guess. So I mean, this portion doesn't work anymore because yeah. So I mean, we're supposed to correct the problem and then have some other type of execution. So it's really the new. So we can write the new executor, I guess. So executor 2. To begin with. So what this is supposed to do is basically terminate when the pointer is outside the list's length. So that would be if program so if well, something like that. So this would be our new breaking criteria, I guess. We don't really need the trace anymore. We're supposed to fix this instead prior to this executing. So we can safely remove that from our execution too. I'm trying to just do some mild coding here while I think of how to approach this problem. So this should be like how we want to execute this program, and we expect us to. So, okay, so I think there's two ways to reason about this. I mean, we could be lucky to just. So looking at the example, what they did was change this instruction to a loop instead of jumping back to this instruction and then jumping back and then jumping forward and ending up in an infinite loop. So what happened here, and in the real jump 4, we add this, we jump back, and then we add that one and we jump back, and then we're at our infinite loop. So it's not clear that it's like one of the last transactions either. It could be, or one of the last instructions either. It could be pretty much any jump or loop instructions in the code. So let us inspect. But I mean, it's pretty, seeing that we want to end up outside the program for it to terminate, it either has to be a jump instruction high up that, well, I mean, it could be natural progression as well. But so the obvious one is like we run into some sort of fence that turns us far down into the program that jumps back and gets us into the loop eventually. So I guess what we could do is to traverse backwards. So if we have our list with our program, or we have our instruction set, and we have an execution path where we're jumping around into our program, and the pointer comes back and says, well, this ended up being an infinite loop. What we could do then is traverse that series, or in that trace, and change the last jump instruction, or the last loop instruction, the first loop or jump instruction we find, and change that. So that's probably a pretty good idea. Okay, so this actually, so the trace here comes into handy, I think. Yeah. Okay, so my idea here is that once we're done here, so we execute this first, that gives us a trace. So that's basically the trace that gives us a loop. And we want to change one instruction in this. So the obvious way, or obvious, I'm not sure, but one way of doing this would probably be to just grab the last instruction of the trace, look at that instruction, and then, well, this was XY, or this was a noop. Let's try to change that in the program to accumulate, or a jump instead, and then execute the program again and see if we get into this problem yet again. So I think this is a good way of approaching it. So so the trace here gives us a list in the order. Let's see here. So this would probably be the reverse order. So we want to return the trace as well. So let's add the trace to our state just for convenience. Trace, which is a list. Well, yeah. List. List of ints, which is our pointers. I guess I just, for clarity over here, so this kind of becomes messy, I guess. But so this kind of becomes a stack. Our latest executed instruction is at the front of the list. To this, we also, well, just let's leave this as is. I guess we'll rewrite the execution function later. Okay, so we have our trace. Let's delete it from there. And in here, we'll add our trace. And we'll initialize this as an empty list. Let's also change this back, so we are dealing with a small program here. In our second, we wanted to end up with 8. Port 2. Yeah, so we have our state, we have our trace. Into our trace, we add, so this is state.trace. And here we'll we'll remove this. Okay, let's see if this still works. We'll just uncomment this. Oops. If trace, right. State.trace. Register. What line are we? 43. Program exec 0, pointer our state, and a list. Oh, right. So we still have our old trace there. Okay. More errors. Where is this? 48. Didn't I comment this? Right, so we have 5. So that's our original answer, and just so let's well. So this gives us that, and now to work with our second portion. Right, so we had our trace 4, 3, 7, and so on. So we jumped around before we terminated. And if we print this. Yeah, so we'll see that this is a stack. We probably should include here our last pointer. No, let's not, because the last one, the 4 instruction, is what brought us back. So that's probably the one we want to start, iterate, and change. So it's somewhere in this trace that I assume that we want to change one instruction from one to another. So I guess this is a kind of an iterative process. So let's rewrite our exec2 program. We have our state, which we kind of redefined. And we want to do 2 checks here, I would say. So we'll just define another type here, and success, it's a bool. Okay, so in our state, which is our expanded state that we just added, we want to do 3. There's 2 different ways that this terminates. Either the program, the pointer, it's larger than the length of the program, so we can't find that one. And I guess so. The pointer would be. The length of the program is smaller or equal to the pointer. So that would be one way to terminate the program. The other way would still be the same as we did on the other one up here. So if the state dot trace exists in the or the pointer that we're seeing exists in the state, then we're also supposed to terminate. But if this is true, we want to just add some extra information here. So success is now true. Was that what I? No, success. The autocomplete is not too great. So that is what we want to do there, and if this happens, it fails. There. Okay, so let's try this program again with our new state 2. Let's call it, well, let's not call it anything. Log. So this will return us our state, whether the trace, whether it succeeded or failed, and we also have to add success which is false. And we only care to up this state if it actually succeeds and it terminates as a regular program should. So I think we have to add this here. Noop just returns a state. Accumulator. Yeah, okay. So let's try this. No more errors. Yeah, so the accumulator. Some record fields are undefined. Success. Doesn't it? Oh well. Let's just... Let's not just deal with this. And we'll add... So in this case, we don't really care about this in the first state. So that's just finding the actual trace. Well, I mean, we could probably use this function for this one, but let's not at the moment. So we'll just have to add some of this extra thingies. Fails 53. Oh. There we go. So okay, so the accumulator returned 5. We success was false. So this is good news, or at least this is turning us onto something. So the idea now is to use the state from the original trace to work backwards. So what we want to do, I think, is to reduce over this. List.fold. And we want to fold from the left, seeing that we want to pop things off the stack. And if this is something that changes, then we want to change one instruction in the program and toggle that one. So let's so here we have the accumulator, which I'm not really sure what it is at the moment. We have the instruction that we might want to change, and let's call this the basic state. There we go. So in this accumulator, or in this fold left, we take the accumulator, which is our state. So let's just change that to state. So well, okay, let's general. There's a lot of states going on here. Let's, to make this clear, no, we have more. Let's just call this accumulator. Okay, so the idea now is that we're at I, and we want to inspect that part of the program or that instruction. So this points to instruction number 4. So if that instruction is a noop or a noop or a jump, we want to toggle those. So I think that is basically it. And then we want to do this and try the program for each time we change this. This might be a brute force way of doing it, so I'm not sure if it will work, but we'll see. So we have to change our program. So list dot, and now I'm kind of wondering how I change one particular thing in a list. Is there like a set? For all, find all. Returns the nth element, but we want to set the nth element to something. How do we do that? Do I have to do some... I mean, I probably could just do it with the map and just replace it when I is equal to whatever we're looking for. But that seems kind of baroque. Partition. So we probably also could partition the table and then join them together again. Remove mem, same as sock, simply returns. We want something that returns a list. Okay, I'm not sure how to do this in Reason. If we were to use a wait, can I do... What happens if... okay, let me just... Can I do like program... Would that do something? No. No, so that expects... So I think arrays in general are immutable in... Or are mutable in Reason, while lists are not. Okay. So we'll do something. I kind of just thought of another thing. If the pointer happens to be actually negative, we kind of want to do the same thing here. So if the pointer is less than 0, we also, because I mean this would obviously, it might mess with the program in general that it jumps outside pre-stack, and so that would probably also be a return statement over here. Okay, sorry for the slight detour. Yeah, so we want to replace one item of the program. So the program is, we pipe that into new program lit map I, that gives us an integer, and that gives us a program inst. So if I equals I, the instruction that we want, so I is the instruction up here that we might want to change. So if we find that one, we might want to do toggle things here. Toggle to give us a new program to try to execute. Else we probably just want to return the instruction just as is. And so how do we want to toggle this? So let's do a switch on the instruction. So if this happens to be a noop, well, a noop of I will toggle this to a jump of I, and if this is a jump of I, we toggle this to a noop of I, and otherwise, can I do, well, otherwise we'll just return the instruction itself. So this will, so what this will do then is if, so when we get to this, for this new program, in each fold we will go through the trace, and then for each fold we will map the program and just replace one item basically. So this kind of becomes a quite expensive or quite weird way to just replace one item with something else. But we're happy with that for now. And so this is what we do. And now we have our new program, and we want to execute this as well. Yeah, so we're at part 2. So here, so we want to execute our new program with the same initial values, with the same trace and success, and we call this exec2, right? Exec2. So I guess this now, so this will return our new state. Our new state. So now it kind of comes into something like if n state success. If that is true, then we'll in the reducer we'll just replace the old state with the new state. Otherwise we will keep the state that we got in from the accumulator, which has the false and the 0 and all that. So what this will do is now that it will fold, so it will loop over the trace for each instruction that we find. We try to replace just that instruction in the program, and that's what this is supposed to do. Fold left. Yeah, right. Yeah, okay, so the trace is what we fold over. Yeah, that's right. Okay. So this will end up being our new res. Well, let's just log this and see what happens. So I mean, if this goes well, we should find one state, and I mean, if we find this, so we probably could do something like this. If uc.success, then we'll just return accumulator. Now we kind of otherwise we'll do this stuff. So we'll just, once we found a solution, we'll just short circuit this whole ordeal. So it kind of becomes somewhat messy, this. Yeah, okay. So in this case, it was supposed to return 8. So let's see what happens. Oh no, more errors. So here we do execute exec2. Warning, unused rec flag. Don't recurse. Oh, okay. So recurse over the wrong function here. And what was the other error? Else inst. If I equals I, and the instruction, there is a instruction set with the pass through map I. Okay, what does map I take? It takes an int and an element. So this should be correct, I feel. And inst would be the... So why wouldn't I... Inst can't be found. Oh! My dyslexia hits yet again. If n states yet again. Fat fingers all around. Okay, so this seems to be not working too good. Yeah, not supposed to take that long for 4 or 5 instructions. All right, time for another beer. Okay, so what is happening here? I probably should just rename this thingy. Or remove this. So let's call this I element this. So in the list where this is I, let's comment out this for now. So let's just try this. List set 1, so that will be this one, hopefully, with 10. Oh, right. So that's the element, and if I... This we have to... Okay. If I equals II, then... So this seems to be working. Let's just clean up this part. Map by, there we go. Okay, so now we have a list set. We could change this to 0. And that would change that one. Yeah, okay. So now we have our list set function. That might help us out a little bit to clean up the code to see what's going on. So we have our fold left. If we have accumulator success, then we'll back off. If we otherwise, we'll make a new program where we end set. So I here is the instruction that we want to replace. So the question is what we want to replace this with. So we'll do another else if here. So else if program, program or list.nth program and I. So if that happens to be accumulator, does this work? Of anything, we just keep going because we know that that doesn't change anything. Otherwise, so we haven't succeeded yet in our fold. We haven't we're not looking at accumulators. Then we want to create our new program, which then would be a program and our list. We want to flip this instruction. And then we had our switch. So our instruction is this thing here. And our new program, so we want to flip this. So now we're supposed to know, well, And now we want to set our instruction, and what was the syntax? So I, the element we wanted to change, which was I, and we want to change the instruction. Okay, so I can't do that. Does this work? Can I do comparison? Why is this a thing? Do I have to do like equals 1? So it's happy about that, but it still doesn't really make any sense. Okay, I'm not sure how to solve this, but so let's do it down here instead, I guess. So we have our instruction, and we do our switch over here. And we'll do another switch. So if this is we'll just return accumulator, and otherwise we'll do this whole thing. I'm not sure. There's probably a more efficient way to actually doing this. Okay, so the new program then becomes, we'll change the instruction on that place, and we execute the program, and we hopefully get a success, and then we get an end, and then we change the state of that one, and otherwise we continue with our accumulator. So let's just make this, I'm not sure if it's more readable, but smaller, less nested, I guess. So I guess this is what we want to do. It still kind of enters some sort of spin lock over here, so I'm not really sure what is happening. So if I add a 0 there, we probably should terminate quite quickly. Yep. Is this the problem, maybe? Nope. So if the program length of the program is blah, blah. Oh, right, we don't update our state, so that we or our traits rather. So that's why we get into our problem. So the state, let's state equal. So here we add our accumulator. We just add our state. Add to the accumulator, we add to the pointer. Yeah. So this state should be state, and we'll add our trace. Is that what we're calling it? Yeah. Trace is equal to state dot trace list dot append pointer. Okay, so this should, oops, what did I do? Yeah, so we override our state with our new state, and that's the state that we use, so we actually know when to terminate. Okay, failure nth. So we're trying to get something outside of bound. So that's here. And that would be if this one failed. If pointer is bigger than length. Bigger equal. Yeah. So now we have 8 as our accumulator, and that was what we were looking for in our sample program, right? Which is 8, yeah. Okay, so folks, I think we're nearing an answer. I'm hopeful anyways. So let's replace this with data.string and see what this yields. So this yields now a successful exit, which is nice, and 1375. So let's see if that is correct. And it is. Oh, so this was interesting. I haven't really. It was a long time since I was in college dealing with these types of problems, I guess. But it's always nice to get back to it. Ooh, get some nice smileys in the chat. So I guess what's left for me is to do some cleanup before I push this to my Git repository. I'm not sure if anyone's interested in it, but you can find it here, where I've remade some old, restructured some of the old ones. Yeah, so I guess this is it for today. Unless you guys want to see me. Well, the stream has been going for an hour and 10 minutes. I thought this was supposed to be like an easy one again after the yesterday's graph problem, and the first portion really was. I felt that was quite intuitive how to solve, but the next one was quite interesting. I'm not sure if there is a better solution, like some speculative thing, but so I mean it kind of boils down to, in this case, that I'm traversing the stack or the trace backwards and just trying to replace one instruction and see if that runs, and trying to replace the next instruction and see if that runs. So it doesn't really feel too sophisticated, but well, it is what it is, I guess. Yeah. Happy days. Anyone? Nothing? Okay. So, yeah. If you want to view it or see the cleaned up version, it's probably going to look slightly different. You find it at my Git repository. Alright, until next time, I guess. Bye-bye, guys. Always a pleasure.